other key words. So vertex, where is the vertex on this graph? Good, Guillermo. -2, 17, all the way up here. There's my vertex. So it's at -2, 17. And as a reminder, the vertex is the point where the function turns, like it kind of changes direction. If you think of this kind of like a roller coaster or a hill, right? The function, it's going up, 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 and down. So it goes up, it hits the vertex, and then it comes down. So that's what the vertex is. It's the place where the function kind of turns, goes in a different direction. Where is my axis of symmetry? I think Guillermo's got it already, -2. Good, so the axis of symmetry cuts the parabola in half. It cuts it right in half. And when we want to say the name of the axis of symmetry, let me actually do this in this color. If I ask you, okay, what is the name of the axis of symmetry? There's my axis of symmetry. You want to give me the x value that it passes through. So if you look, well, you can't really see it now. Let me go back to using the highlighter. So if you look, the axis of symmetry is passing through the -2. So when I ask you where is the axis of symmetry, you're going to say it's at x equals -2, because that's where it's passing through. It's passing through the -2 on the x-axis. So that's my axis of symmetry. And what it does is it basically cuts the whole parabola in half. Any questions on axis of symmetry? All right, cool. Now on this graph, do I have a maximum or do I have a minimum?
A maximum.
I have a maximum, and Guillermo already got the answer for us. The maximum is located at y equals 17. So when you look for your maximum point or your minimum point, you want to see where is it passing through the y-axis. So if that's as high as the graph goes, it's not going to go any higher than that. And if you look right here, well, it doesn't say 17, but you can see that it's passing through the 17. So the maximum on this parabola is at y equals 17. And you want to be very careful with these problems, and you have to know that the answer, it's not just 17, it's y equals 17. You have to be very specific, because if you just say 17, I could be looking at the x-axis instead of the y-axis. So you just want to make sure that when you're giving me the answer for axis of symmetry, you say x equals whatever. When you're talking about the maximum or the minimum, you want to say y equals whatever. All right, so we've got maximum, we've got axis of symmetry, we've got the vertex, and Guillermo's on a roll here. He's giving us the rest of the information. We also have a y-intercept. Now, I want you to take a look again at the y-intercept. What do you think it is?
It's 10 because it's in the middle of the 8 and the 12.
Oh, so maybe it's not 17. We got to look at a little bit more carefully, because what is the y-intercept? What does the y-intercept do?
It's the number when it touches the y.
When it touches the y-axis, exactly. And you can see that it's crossing the y-axis right here at that point. Okay, so you got to look, it's not going to be the same as the vertex. Sometimes it is, but not always. So you want to look at where is it crossing the y-axis. That is where your y-intercept is located. So my y-intercept is at 0, what is that, 10? Oh, it's going by twos. Oh, it's going by twos. So actually I made a little mistake. Where is the maximum? It's not at 17, it's at what? Because it's going by twos.
18.
That's 18, yeah. And the vertex would be -2, comma 18, not 17. My bad. Okay. So y-intercept 0, comma 10. X-intercept, is there 1? Is there 2? How many are there?
Two.
Yeah, there's 2. It's crossing it 2 times. Where?
And -5 and 1.
-5 and +1. Good. So at -5, comma 0 and 1, comma 0. So it's got 2 x-intercepts in this case. Now, x-intercepts, I want you guys to write this down because we're going to be talking about this a little bit later in the week, but you might see it come up before that point. So I just want to make sure we all know. X-intercepts have 2 different names. Sometimes you might see it be called the zeros of the function. It's also called, sometimes they call them the solutions of the function. And again, we'll talk about why a little bit later in the week. You'll understand exactly why. But just look out for those words, because if you see the word zeros, if you see the word solutions, you know that it's talking about the x-intercepts. All right, so that's everything. How do we feel? Any questions? Okay, cool. So we're going to do a couple more examples of the same exact thing, and then we'll move on to new information. So if you were kind of still catching up and you weren't so sure, hopefully you'll feel a lot better in the next 3 slides. So let's go ahead and go through it. Really quick, I just wanted to review one more time what exactly is a quadratic function. So you guys, if you were here yesterday, you already wrote this down. You do not need to copy it again, but I just want to quickly review it. A function that can be represented in the form f of x equals ax squared plus bx plus c is called a quadratic function. And I don't think I talked about this in my period 2, so really quickly I just want to point this out. And if you're in my period 8 and you already saw this yesterday, give them a chance to figure it out first before you give away the answer. What is this? So I copied this from right here, but it should look pretty familiar because we've been seeing very similar things all week. What is that? What type of expression is that? Someone said it looks like from foiling. That's a very good clue. So think back to foiling, and then after you foil, you get an answer. And what is that answer called? It's a type of expression. We've seen it's all we did last week. Everything we did last week. All week. This is all we did. I'll give you a different one. I'll put numbers in there instead of variables. What is that?
Exponential function.
It's a trinomial. It's a trinomial. Good. It's not an exponential function. It's not an exponential function. It's a quadratic function. Exponential functions, what's the difference? This is an exponential function right here. What's the difference?
Wait, quadratic function is the one that have polynomials?
Mm-hmm. Yeah. What's the difference between up there, the trinomial at the top, which is a quadratic function, and then down here, which is a exponential function? What's the difference? It's not a trick question. Just look very basically. What's the difference? I'll give you another example. Here's a quadratic. Up there is an exponential. What's the difference? There's more than one difference. I'm sure anybody can point it out. What is one thing that's different? Again, it's not a trick question. A 4-year-old could tell me the difference. Okay, I'm seeing in the chat, exponential functions look shorter. Quadratic functions, they're not doing multiplication. But even more basic than that, think like the most obvious difference between these two types of functions. Okay, exponential functions don't have addition. Okay, I'll make it very obvious for you guys. What's the difference? What's the difference?
Exponential function has a variable for an exponent.
And quadratic function has a
Number.
And specifically the number is 2. It's not going to be anything
It's
higher than
for
that.
squared.
Squared, exactly. That's the difference. That is the big difference, okay? So it all comes down to what is the exponent. If the exponent is the letter x or the letter t, right? That's an exponential function. Because if you think about it, the name exponential has the word exponent in it, right? So that's one way to remember. Exponential functions have an exponent of x. Exponent x. Quadratic functions, quad, what does quad remind you of?
4.
4, what has 4 sides?
Square.
A
And a
square.
rectangle.
Yeah. Think of a square. Square, 2. Power of 2. Okay? So that's one way to remember the difference. So quadratic functions are squaring. That's why you have a 2. Exponential functions have an exponent of x. Okay? So that should really clear up a lot of confusion that sometimes people have between exponential functions and quadratic functions, because I agree that they look similar in a lot of ways, but the big difference is that quadratic functions have an exponent of 2 and exponential functions have an exponent of x. Any questions on that? Cool. Okay. So, and also obviously their shape is different, right? Because we know exponential functions, they look kind of similar, but exponential functions look more like this. So the big difference is that quadratic functions, they come down and they go back up, but exponential functions, they just go in one direction. They go up, and on the other side, they kind of stay like they're reaching towards 0, but they're never going to come back up. All right. Any remaining questions or anything about the difference between exponential functions and quadratic functions? Cool. Alrighty. And the one other thing that we highlighted yesterday is this part right here. So the most basic quadratic function is f of x equals x squared. And so that is my parent function. F of x equals x squared. What is the leading coefficient of the parent function? So what is the leading coefficient of this function, the parent function? I'm seeing it in the chat. Feel free to say it out loud. The leading coefficient. Good, it's 1. There's an invisible 1 out in the front. The leading coefficient is 1. And I have it graphed right here. So this right here is the parent function. The leading coefficient is 1. What's the y-intercept? Or no, where is the vertex? Where is the vertex? I'm seeing one person in the chat, but everybody at this point should be able to tell me where is the vertex on this graph. Send it in the chat or say it out loud, but I want to see way more participation than I'm currently seeing. Where is the vertex? We just went over that.
The origin?
The origin, good, 0, 0. So those two facts are very important about the parent function. Okay, the parent function has a leading coefficient of 1, and we'll talk about why that's important in just a little bit. The leading coefficient is 1, and the vertex is at 0, 0. So if there's nothing else that you remember, oh, and then actually one more thing. Does the parent function open upwards or open downwards?
Downward.
This one opens down?
Upward.
Upwards. It's a smiley face. So it opens upwards. Okay, those are the 3 most important things about the parent function. The leading coefficient is 1, the vertex is at the origin, and it opens upwards. Well, and I'll explain why that's important in just a little bit. But do I have any questions on those 3 things? Okay, cool. All right, let's do a few more examples just to really get an understanding of how to do this. So let's see how fast we can do it. And I want to see how many people can participate. So send me your answers in the chat. That way I can make sure that everybody's on board. Vertex, where is that? Go ahead and send me your answers. All right, give you guys 10 more seconds. I'm seeing a few responses. 1, 2, 3, 4. I have 4 responses so far. Where is the vertex? All right. RL, can you please share your answer out loud, please?
3, 4.
3, 4. Right there. It's the tippity top. 3, 4. When I ask you for the vertex, you have to give me a full coordinate point. A couple of people just said 4, but 4 can be anywhere. I don't know where 4 is. 4 could be over here. 4 could be down here. I don't know. It could be over there. It could be this 4. It could be down here. If you just say 4, you're not giving me enough information. So when I ask for the vertex, I need to know the full coordinate point. Full coordinate point. 3, 4. Any remaining questions on vertex? I want to clear it up now before we move on. Any questions? Okay. Next one, send it to me in the chat. Privately is just fine. Where is the axis of symmetry? Where is the axis of symmetry? Go back to the previous examples we've already done. If you're not so sure, hopefully you wrote them down. Go back to those examples and see if you can figure it out. Because right now I only see one response. That's a problem. That's a problem. Okay, I see 2 responses. All right, so since I'm only getting 2 responses and I see 13 students in this class, does that mean that I have 11 students that are absolutely clueless, like zero idea how to do this? Zero idea. No, couldn't even describe it using words. Because if that's the case, then I have a completely different issue to deal with. I have 2 scenarios. Either I have 11 students who are not paying attention to me and that's why they're not responding, or I have 11 students who don't know how to do it and that's why they're not responding. So if you don't know how to do it, let me know. Say, Miss, I don't know. I would rather you tell me that, because otherwise I'm going to assume that you're just not paying attention, that you fell asleep or you walked away, you went to the bathroom, you're making breakfast for yourself. I don't know. I don't know what's happening on the other side. All right. Karina, can you share your answer with the class, please? Where is the axis of symmetry?
X equals 3.
X equals 3. At X equals 3. Like I kind of explained this before, but I'm going to keep explaining it till it makes sense. The axis of symmetry cuts the parabola completely in half. There's my axis of symmetry. When it does that, it passes through the 3 on the x-axis, right? You see how it's passing? You don't see the number 3, but I know it's there. It's passing through the number 3. So for that reason, we say it's at x equals 3. Do I have questions on axis of symmetry? I'm giving you the opportunity now. So don't go back and say that you don't know how to do it when I'm giving you the chance to ask your questions right now. No questions. It just cuts through, exactly. The axis of symmetry just slices everything in half. And then you just look, once you look at where the axis of symmetry is, you just want to find the number that it's passing through. And it's passing through x equals 3. So that's what we call it. We say that the axis of symmetry is at x equals 3. All right? Okay. Do I have a maximum or do I have a minimum? And then tell me where it is. Again, do it privately in the chat. I want to see as many people participating as possible because I want to make sure that you're paying attention. Where is it? What do I have and where is it located? And if you can only answer one of those two questions, that's fine. I don't mind if you don't know, that's fine. But I need to see that. I need you guys to tell me that so that I know who's paying attention and who's not. All right, 10 more seconds. Do I have a max? Do I have a min? And where is it located? All right. Let's see who got it this time. RL, can you share yours again, please? What is it and where is it?
It's the maximum. It is at -4. Or you go 4.
4, good, +4. It's a maximum. It's a tippity top, not tippity bottom. It's the same place as the vertex, but when you give me your answer, now you're just telling me the y value. Just the y value. So actually, if you're not sure what the y value is, you can actually look at the vertex itself right here, the 4. That's where the maximum is located. So the maximum is at y equals 4. Because what's happening when I ask you for the maximum, think about it like it's the ceiling. It's as high as it's going to go. That is as high as it goes. And that purple line that I'm drawing, it's passing on the 4 at y equals 4. So when I ask you the maximum, I'm asking how high on the y-axis, how high does this function go? What's the highest point that it reaches on the y-axis? Questions on maximum or minimum? So the vertex is a coordinate point, and then the axis of symmetry is x equals, and the maximum or minimum is y equals. Questions on those 3. Those are the most important things. Like if you still aren't sure about them, I need you to ask me your questions now before we move on. Okay. Question? Maybe? Is the vertex where the line crosses the y-axis? No. Go back to your definition of vertex. Can anybody tell me what the
Where
vertex
it
is?
turns.
It's where it turns. It's where it turns. It's the tippity top or the tippity bottom. Is the maximum / minimum always the vertex? Yes. Yes. Always. So if you're not sure where the maximum is or where the minimum is, go to the vertex. Go to the vertex and look at the y value of the vertex. Max is y, min is y. Yes, both of them, the maximum and the minimum are both the y value. And in fact, if you go back to your notes from yesterday, you wrote this down. It should be in your notebook. We wrote down the maximum and minimum is the highest or lowest y value. So it's always the y value of the graph. And like I said before, it's always at the vertex. So they're basically the same thing. The vertex and the maximum / minimum are basically the same thing. The only difference is that the vertex is the full point, the full coordinate point, whereas the maximum and minimum is just the y value, just the y value. Same thing with the axis of symmetry. The axis of symmetry is always going through the vertex, right? So here, let me make this very clear. My vertex is at 3, 4. The 3 is the same thing as the x, the axis of symmetry. So this 3 matches that 3. And this 4 matches that 4. You see that? So that's why those 3 things are all related to each other. The vertex, the axis of symmetry, and the maximum/minimum are all related to each other because they all come down to where the vertex is located. Does that help? Any other questions on that? Okay. Now moving on. Where's the y-intercept? Go ahead and send it to me in the chat, just like before. Good. Lauren, can you share your answer, please?
-5.
-5. Now, with the y-intercept as well as the x-intercepts, just be careful. Again, I want to know the full coordinate point because if you just say -5, I don't know where that's going to be. Is it 0, -5 or is it -5, 0? So if you just say -5, that's okay, but just make sure going forward that we're being very specific. So it's at 0, -5 right here.
In the maximum, there's only one number. It's not the whole coordinate.
Exactly. Yeah. Okay. And then finally, the x-intercepts. Go ahead, share that with me in the chat as well. Where are my x-intercepts? All right, let's see. Alyssa, can you share it either out loud or just type it publicly in the chat for us, please? 1, 0 and 5, 0. So same thing, like I just said, make sure you give me the full coordinate point. And in this case, it's 1, 0 and 5, 0. There's 2 of them. All right, so that's everything on this graph. And it is a lot. I mean, obviously you guys can see there's a lot on this screen, right? So it's a lot to keep track of, but the more practice we get, the more you're gonna, all those little questions you might have are gonna clear up. But do I have any questions at this point right now? All right, let's do another one. So take everything that we just learned and now let's see how much better we can get on the next problem. Take a look. I will admit this one's slightly more challenging down here when we get to these two, but that's okay. Just remember what I said, vertex, axis of symmetry, and maximum/minimum are the most important. So see how easily you can get those. I'll give you guys about a minute. Send me your answers in the chat. Vertex, axis of symmetry, and max/min. All right, take about 10 more seconds. All right, good, 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 good. I'm seeing good answers in here. Let's check it out. Karina, where is the vertex?
4,3.
4,3. There it is. There's my vertex. Let's see. Lauren, where is the axis of symmetry?
At 4.
At 4. Now, let me highlight it. I'll do it in green. There it is. Now you got the right answer, but let's be a little more specific. It's not just at 4. 4 can be anywhere. It's at x equals 4. So it sounds like it's not important, but it is very important. X equals 4, just so that we're being specific about which 4 we're talking about. So axis of symmetry is at x equals 4. And let's see, I haven't seen the correct answer yet for maximum or minimum. So go ahead, if you haven't sent it yet, send it now. All right, Samantha, do I have a maximum or do I have a minimum?
Minimum.
I have a minimum, good. I have a minimum. Remember, it's at the same exact place as the vertex. I have a minimum, and where is the minimum located? Lauren, where's the minimum located?
When y equals 3.
At y equals 3, good. Again, where do we look? We can look right here. Here's the 4. Here's the 3. Oh, that's ugly. Let me do this in black. So it all comes back to the vertex. If you know where the vertex is, you know that the axis of symmetry is the x value and the minimum or maximum is the y value. So again, any questions on those 3? Okay. Now, the last 2 I said was going to be a little challenging. That's because it's a little hard to tell on this graph where the y-intercept is going to be. So we're going to skip that one because you can't really tell, like this is going to keep going and the y-intercept will be somewhere up there, but we can't really tell where it's going to be. So we're just going to skip that one. But x-intercepts, let's think about that one for a moment. What do you guys think? Is this graph going to touch the x-axis?
No.
No, right? Because what's going on? What's going on is this graph is going to go up, 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 forever. It's not going to come back down. And the minimum is at y equals 3. So the minimum value, that's as low as that graph is going to go. It's never going to go under that. So what that means is that there are no x-intercepts. So we can actually write that answer. There is no x-intercepts. Now remember, x-intercepts, we call them by different names. So what I would write is there is no solutions.
Miss, will it eventually touch the y-intercept?
Yes, yeah. If you kind of extend this, you can tell like somewhere up there, I can't tell where, but somewhere up there, it's going to be crossing the y-axis. So probably around like the number 15 or so, maybe 20. But I can't tell where it's going to be. So there is a y-intercept. I just don't know where it is yet. Any other questions? So again, when there are no x-intercepts, if there's none, we call that no solutions. All right, check it out. Any final questions? We are going to do one more, but are there any questions right now? cool. I wanted to do one that is a real world scenario. So here's another parabola, but this time this graph actually represents something in the real world. It's the height of a flying disc over time. So, but the same questions apply. Take a look. If you have to estimate it, that's okay. But see how many of these you can answer. Go ahead. Take about 2 minutes to get as many answers as you can. And same as before, start sending them in the chat for me so that I can see how much we're understanding. All right, about 10 more seconds. Give me your answers in the chat. Okie dokes. All right, Guillermo, where's the vertex? You can either say it out loud or type it publicly. Where is the vertex? 5,20, good. Vertex right here, and that's 5,20. Okay, Lauren, where's the axis of symmetry?
When x equals 5.
At x equals 5, good. So we cut this right in half and it passes through the 5. Karina, where is the maximum?
Y equals 20.
Y equals 20. The highest possible value that this graph is going to go to is 20. All right, so those three, awesome. Now, here's where it gets a little bit more challenging because we are going to have to estimate a little bit. Y-intercept. Let's think about that. Do we see a y-intercept on the screen?
No.
No, right? We don't see it. It doesn't exist on the screen because what's happening, if I extend the y-axis downward and I extend my graph downward, okay, eventually it's going to cross the y-axis, right? But it's off the screen, it's off the graph. But what type of number is that going to be? Approximately, what does that look like? Like around what number?
Probably -2.
-2.
Yeah, around -2, somewhere around -2. But let's actually think about this for a moment. I'm talking about the height of a flying disc. That's like a, what's it called? A frisbee, a frisbee. Is that frisbee gonna go negatively downward under the ground?
No.
No,
No.
right? So this is where we gotta kind of think about the real world. So technically, there is a y-intercept, but it doesn't really make sense in the real world. So for y-intercept, you can say it's at 0, -2, but it's not what we call viable. So the word viable just means that, like, can it happen in the real world? Yes or no. Is it viable? Does it work in the real world? If it is viable, then it works in the real world. If it's not viable, then it doesn't work in the real world. So it's not reasonable. Yeah, that's another way to say it. Exactly. So there is a y-intercept, technically, mathematically there is, but it's not viable. It's not actually going to work. Not reasonable. Does that make sense? Do I have any questions on that? Awesome. Okay, and then x-intercepts, they exist. We might have to kind of estimate them a little bit. And Alyssa, you have some great estimates. Can you put them in the public chat, please? Good. 0.5 comma 0 and 9.5 comma 0. So like right here and right there. Somewhere in between 0 and 1, and then somewhere between 9 and 10. Right? And if you think about it, that's where the frisbee starts. So it's on the ground, I guess. Kind of weird. I feel like a frisbee shouldn't start on the ground, but okay. So maybe they kicked it, I don't know. But it starts on the ground, they kick it upwards, it comes back down, and it hits the ground again. Questions on this one? Feeling a little bit better about all these words, all these different terms? Anyone have any final questions on it? This is the last one we're doing. Okay, I'm seeing some thumbs up. Good. Alyssa feels good. Karina feels good. Guillermo, not sure. Okay, Guillermo feels good. Everyone else, not so much? What's going on? Okay, we'll continue talking about all these words, but if you're still stuck about what they mean, definitely go back and watch my videos, and where, especially the video from yesterday where I wrote down all of the definitions. So if you're still not fully understanding, go back to that slide, watch that slide again where I go over the definitions and just review that, okay? Because we have to move forward. Okay, so I have 3 graphs on the board. On the first graph is my parent function. There it is. This is the parent function. And remember, we wrote down some important information about the parent function. Okay. The vertex is at the origin. It's at 0, 0. It opens upwards. And what's the leading coefficient again?
1.
It's 1. 1. So the leading coefficient is really, really important because it kind of changes the graph. It changes the graph. And the leading coefficient, we have a name for it. It's called A. So look up here in the corner. A represents the leading coefficient. So in this case, my leading coefficient is 1. So I say that A equals 1. The A is the leading coefficient. So let me highlight that over here. Okay. Now, you don't have to copy these down. I just want you guys to take a look at the other 2 graphs. And let's compare them and talk about what is different and what maybe is the same when we compare them to the parent function. So starting with the second one, the one in the middle. First of all, what is A in this one? What is the leading coefficient? So this leading coefficient is 1 because there's an invisible 1 in the front. What's the leading coefficient of the other one, of the second one?
2.
It's 2. So we're changing the equation a little bit. We're changing it to a 2. Now let's look at the 2 different functions. What is the same about them? What stays in the same spot?
The
The
x
X
squared.
value.
Say that. Okay, so the equation, the x is the same, x to the power of 2. But the graph, visually, what stays in the same spot?
The vertex.
The vertex.
Yeah. So the vertex is in the same spot. But what changes between this visually, just use your descriptive words, what happens between going from the parent function to this one right here?
The U is kind of like small.
That's a good way to say it. The u is a little bit smaller, a little bit, what are other words we can use? Smaller. What else?
Intercept is like less.
Like less?
Like the X values, they're like smaller.
Yeah, they are. They are. But more visually, like describe the shape of it a little more. So you're right about the X values.
It got skinnier.
Skinnier. That's a really good one. Skinnier. Skinnier. Karina in the chat said it closes up a little more. It's more closed. That's a good way to think about it. If it's kind of like a mouth, like that it's closing in on itself. So when we increase the value of A, the leading coefficient, when it gets bigger, the graph actually becomes a little smaller, a little skinnier. It's like it's being squeezed. That's a really good word. It's being squeezed. I like that. Squeezed. Okay. So those are all very, very good ways to describe it. And if I go even further, let's look at this graph now. What's the leading coefficient? What is my A?
4.
4. So I'm increasing it even more. And what happens?
It got even smaller.
Even smaller, even skinnier, even more closed up, even more squeezed. But does the vertex ever change? No, right? It stays in the same spot. So if you think about like the vertex is kind of where the parabola lives. It lives at the origin. It's just getting smaller. It's getting squeezed tighter together. So I'm going to write that down as well. So even more smaller, more small, more skinny, more squeezed. Okay. So that's all. We're just kind of noticing these patterns. You don't need to really write it all down quite yet, but I just want us to kind of start seeing what's happening here. Now let's look at some other examples. Now I still have the same parent function, same one. We know that A equals 1. We know that it lives at the vertex, at the origin, I mean. And what's happening in these other ones? So for g of x, what's the value of A? What's the leading coefficient?
1/2.
1/2. So now I'm making the leading coefficient smaller. I'm making it into a fraction. And visually, what happens?
It got wider.
It got wider. Yeah. Wider. Same vertex, same exact vertex, but because my leading coefficient is a fraction, it's wider, it's more open. More open. Any other descriptive words? I'm seeing a word in the chat that I'm I'm going to stay away from that word, Karina. You'll see why in like 30 seconds. It's a good word, but it might confuse us a little bit. Okay, so it's more wide, more open, and then kind of similarly over here, what happens when I make it 1/4? A equals 1/4.
It got even bigger.
Even wider, even more open. But like I said, it's still staying at the vertex. So before I go on to the next slide, where I'm going to give you the definition, let's actually see if we can figure it out on our own. What seems to be the pattern about why is the leading coefficient important? What does the leading coefficient do to your graph? I'll go back to this slide so you can look at it again. What does the value of A do to the graph?
It determines how wide or how slimmer your graph is going to be.
Exactly. It determines that was so perfectly said, RL. I'm not even going to repeat it. You said it perfectly. So if the leading coefficient is greater than 1, so any number 2, 3, 4, 5, 6, 7, 8, any number greater than 1, the graph actually gets kind of smaller, like Karina just said. The bigger the leading coefficient, the smaller, the more stretched out, the more squeezed that graph gets. When the leading coefficient is a fraction, so when it's less than 1, or you can say when it's between 0 and 1, so any fraction between 0 and 1, the graph actually gets bigger, it gets wider, it gets more opened up. So now let's actually talk about the definition. Oops. So we have what's called a vertical stretch, and this is what I do want you to write into your notebooks. So we have a vertical stretch. A vertical stretch means that the graph gets skinnier and more closed up. And a vertical stretch happens when A is greater than 1. So the word stretch might be a little bit confusing sometimes. Like for me, the word stretched out kind of always, I never quite understood why they use that word. But I want everyone to think about a rubber band or a hair tie or something like that. Okay, I have one in front of me if you can look at my video. So here's my hair tie when I just hold it normally. When I stretch it, it also becomes skinnier at the same time. So think about that. A vertical stretch makes it skinnier because it's kind of like you're stretching it out this way, like you're stretching it from top to bottom. So when I say vertical stretch, that just means that it's becoming skinnier. Here's my rubber band normally. On the other hand, I have a vertical compression. So if I press down on it, it's going to become wider. You see that? It becomes wider. So vertical stretch makes it skinny, like this, like my rubber band. Vertical compression makes it wider. All right. So if you're a little confused about why it's a stretch and a compression, think about a rubber band. If I pull on a rubber band, if I stretch it, it gets skinnier. If I press on it, it gets wider. So vertical stretch, graph gets skinnier. So for example, if I go in this direction, that's a vertical stretch. Now on the other hand, vertical compression, the graph gets wider. Oops, gets wider and more open. And in this case, the leading coefficient, the A, is between 0 and 1. So A is between 0, and 1. And you can just remember it by saying that it's a fraction. So we have a vertical stretch, and then we have a vertical compression. And it all comes down to the leading coefficient. So when A is a number greater than 1, we have a vertical stretch. When A is a fraction less than 1, we have a vertical compression. And when A equals 1, so my parent function, when A equals 1, it's just neutral. There's no stretch, there's no compression, it's just neutral. So take a moment. There is kind of a lot to write down on this slide, so I want to give you guys plenty of time to do that. And now is a good time to ask any questions as well if you have any remaining questions or things that you're wondering about. All right, I'll give you guys about 30 more seconds, but let me know if you still need a little more time. I'm happy to give you more time. All right, anybody still writing? Cool. Okay, now let's take a look at a different type of transformation. Let's take a look at what's going on here. So again, I have my leading coefficient is 1 in the parent function. A equals 1. What's going on in the second one? What is the leading coefficient? -2. -2. And what does that seem to do? What happens here? Yeah, so it's negative, and when it's negative, the whole parabola, the whole graph, goes from being a happy, smiley face to a sad, frowny face. So remember what we said before. Parent function opens upward. And in this case, we're opening downward. And I want to point out a word that Guillermo used that's a really good word. He says that it flipped. That's a really good way to think about it. So if you think about it, it was a smiley face before, and it just flipped. It flipped over, and now it's a sad face. A sad face. So it opens downward now, and since it's a -2, specifically a -2, what else happens? Not only does it flip, there's one more thing going on because I have a -2. Good, Karina. It's also skinnier. And what do we call that again? It's also a vertical stretch. So there's a flip and there's a vertical stretch. There's two things going on. Now the third one, similar idea. A is -1/2. So what are the two things that are happening in this one? What are the two things? Because A is
Vertical compression.
yeah, vertical compression. So not only does it flip, but also there's a vertical compression. And it's opening downward. So the negative sign, does the negative change the type of, is like whether it's a stretch versus a compression, or does the negative only change one little thing? Yeah. The negative sign, and I'm seeing it in the chat, the negative sign, all it does is it flips it. The actual number, so I have a 2, a -2, and I have a 1/2, a -1/2. The actual number, the value, still does the same thing. So if I have a 2, even if it's negative, if I have a 2, it gets stretched. And if I have a 1/2, even if it's negative, it's still going to make it a compression. So that's something that sometimes gets a little confusing, but I just want to make it very clear. The actual value, the absolute value, whether it's a 2, a 4, a 6, a 1/3, a 1/2, whatever it is, it's going to make it skinnier and wider. But when you add a negative on top of it, it also flips it. Do I have any questions on that? Okay, so here's where we can write down the actual transformation. So we have a reflection across the x-axis. That's what this is called. And that's when you have a negative in the front. When a is less than 0, you get a reflection across the x-axis. So on both of these examples, we have two different things going on, just like we talked about. In this case, I have a reflection and a stretch. And on the other hand, I have a reflection and
Compression.
a compression, exactly. So they're two different things, right? The negative takes care of the flipping of the reflection, and the actual value, the actual number, takes care of the stretching and the compressing. So again, take a moment to write the definition, and you can sketch those little graphs. They don't have to be perfect, but as long as you show very clearly that one of those is skinnier and the other one is wider, that's really all the information that you need. So it's very useful to have these little sketches. But you can always, if you don't have time right now, you go back and you watch the video in order to review. And I'll give everyone another minute or so. All right, take another 30 seconds. All right, is anybody still writing? Does anyone have any questions? I know there's one question coming in the chat, but does anyone else have any questions? Okay. Here's a question. Okay, if we ever get a question like this on the test, will it already provide an equation for the other graphs? Good question. So on a test or a quiz, usually the way that it's going to look is like they'll give you the equation and then they'll ask you what type of transformation happened. And when it asks you what type of transformation, you're always going to base it off of the parent function. So the parent function is like we said, the parent function is the most basic one. It's like the OG. Okay, it's like where all the other graphs go from. So when it asks you, is it a stretch? Is it a compression? Is there a reflection or whatever? You always want to base it off of the parent function. So really what we're asking is, compared to the parent function, what type of transformation is occurring? So with test questions, obviously you always want to read it very carefully just to make sure, but for the most part, it's going to be basing it off of the parent function. Does that make sense? And usually it'll give you an equation or it'll show you the graph and then you have to tell them what type of transformation happened. Even without the equation, you can still figure it out, right? Because even without the equation, using your eyes, you can see that, okay, there was a flip and it's stretching just using your eyes. So we got to train ourselves to do both. You can look at the equation and figure it out that way, or you can look at the graph and figure it out just by using your eyes, both ways. And we always do some practice problems in class, so you'll see what it looks like on a test a little bit more. Okay, moving on. So we've done all the stretching. It's like, you know, we're starting our exercise, right? We did all the stretching, we did all the flipping. Now let's look at what's going on here. This is something that's a little bit more familiar to you guys because we've actually seen this type of transformation before. We have a vertical translation. So let's actually break it down. Let's see what's happening. Here's my good old parent function as usual. And like we said, the parent function lives at the vertex, at the origin, I mean. What's different about the equation for this g of x? What's different? What did they do to change it?
They moved it up.
Yeah, so visually it went up, but just the equation itself, what's different? What did they add?
The 4.
The 4, yeah. So that 4 has a name. That's my k. K equals 4. So before we were talking about the leading coefficient. That's your a. Now I have a k. This is the k. K equals 4. And what happens? It goes up 4 units. The vertex is now at 0, 4. And we've seen this before, haven't we? We've talked about these types of translations. We've talked about it with exponential functions, where the graph, it moves. It can go up, it can go down, and we'll talk about left and right as well. So k equals 4, so that means that it's going to go up 4 units. What about the third one? Now, k equals -7. And lo and behold, what happens?
It goes down now.
It goes down. It goes down from the origin, down 7 units. So from the origin, that's where we measure from. From the origin, if k is a positive number, it's going to go up. If k is a negative number, it's going to go down. Now, do I have any stretching? Do I have any compressing? Do I have any flipping?
No.
No, not at all. It's just moving. It's just moving. It's like, you know, you got your U goes up, U goes down. It goes up, it goes down. It's not getting wider, it's not getting skinnier, it's not moving in any direction, it's not flipping. It just goes up and then it goes down. And that's it. Because did I change the leading coefficient at all?
No.
No. For my first one, A equals 1. For my second one, A is still 1 because I haven't changed it. For my third one, A is also 1. Because the leading coefficient is what changes the direction and the width. But when you add a number at the end of it, it's not going to change the width. It's not going to change the direction. It's not going to make it flip or go crazy. It's just going to move it up and down. That's all. Any questions on that? Okay. So this is a vertical translation. Now there's kind of a lot written down here, but it's actually really good, useful information. But here, let me actually do it this way. So ignore what it says here, because sometimes the textbook makes it more confusing than it needs to be. So we have a K. Now the K is added to the end of it. If K is greater than 1, we go up. If K is less than 1, we go down. Simple as that. That number at the end is just telling me which way to go. Is it going up? Is it going down? How many units? So like we said here, this is a vertical translation. Actually, I'm just going to write it this way. This is going to go up 4 units because K equals 4. Now, on the other hand, we're going to go down 7 units because K is -7. So again, it's just telling us where to go. Vertical translations. So take a moment and write that all down. And then we'll go on to the last thing. We're almost there. I know we got 10 minutes left. We're almost there. Any questions on vertical translations? All right, is anybody still writing? Cool. All right, last thing. We'll come back to that later. Okay, here we go. Last one, last comparison. I bet you guys can already guess what's going to happen in this case. Look at the vertex. Look at the vertex of each of these graphs. That's where we always want to look. The vertex helps us to see where it's going. What happened in this case?
It go right.
It goes to the right. How many units?
2.
2 units to the right. Did it flip? Did it flip?
No.
No. Did it get wider? It's kind of hard to tell in this case, actually. They didn't make They didn't make it very obvious, but what do you guys think? Did it get wider?
Yeah.
Yeah, this is a bad example. I'm realizing it now. It's kind of a bad example because what happened is that they made it go by twos. So if you look at the y-axis, it's going by twos. So it looks wider, but it's actually not. If you actually look at the numbers, they are the same on both graphs. So I feel bad because it's kind of a bad example, but take my word for it, it does not get wider. However, what does happen is it just slides over to the right, 2 units to the right. And look at the equation. What do we see here? What's kind of different?
-2.
Yeah, there's a -2. There's a -2. So it's kind of backwards to what it actually is. It goes to the right, but it's a -2. And that's just something that we've seen that before. We have seen that before. That's just something to get used to. So this is my H. H. We had a K, we had an A, now I have an H. H is -2, so it goes 2 units to the right. And actually, I'm gonna we'll talk about this more tomorrow. This is where it gets really challenging, but really quickly, because I know we're almost out of time. H is 2, so it goes to the right 2 units. And remember, we're always thinking about the opposite. So even though I see a plus sign, here H is -3. We always flip the sign. And again, I know that might feel a little confusing right now, but we'll talk about it. We'll talk about it. Here's my vertex. And in this case, I went 3 units to the left. So A, the leading coefficient, A, is going to stretch, compress, and flip. K is going to move it up or down. And H moves it left to right. And if you feel like this is a little familiar, it's because we've actually done this before. We did it with linear functions and we did it with exponential functions a little bit. But with quadratic functions, we really get into it a lot. So we did it a little bit before, but now we're like really going to get into it. So one last slide, one last definition. Again, ignore what I have here because I just want to write it down. Okay, so H is this number right here. You have to remember to flip the sign. You have to remember to do that. But once you flip the sign, if H is greater than 0, it goes to the right. And if H is less than 0, it goes to the left. And here are my 2 same examples. We go to the right 2 units. H equals +2. We flip the sign. And we go to the left 2 units. Again, we flip the sign, so H is -3. No stretching, no compressing, no flipping. All we're doing is moving from left to right. So we got through all of our different transformations. Of course, tomorrow we're going to continue with it. We'll review it. We'll do practice problems. You're going to get really good at it tomorrow. For now, we just have a little bit of an introduction. So if you're still feeling a little bit like you need a little bit more practice, you will get that tomorrow. Okay, I will make sure of it. But are there any quick questions now? Because I know the bell just rang at school, but there's still technically 4 minutes left. So does anyone have any questions? Oh, never mind. Okay, I guess it didn't ring. Okay, David. Any questions on vertical translations? Oops, this is not vertical translations. Miss Lopez didn't change the sign. This is horizontal translation. horizontal. Any questions on them? All right, cool. So as a reminder, there is an assignment on Khan Academy. It's already there. It's due Friday, and by now you've learned everything you need. Okay, so I remember yesterday I said you should wait until today. So now at this point, you have everything you need to get that assignment done. So go ahead and make sure that you get it done. It should be pretty simple. It's very, very introduction, just very basic. So try and get it done as soon as possible. It's due on Friday because I will probably be putting up another assignment tomorrow. So just the sooner you get the first one done, the more time you'll have for the second one, all right? So awesome. Have a good day, everybody. I will see you all tomorrow. Bye, everyone.
Bye.
Bye.